Good morning or possibly afternoon. My name is Ben Gagliardi. My talk today is Transition Matrices from AOTTP Bigeye Tuna. I'd like to acknowledge my co-authors Igor, Nicola, Marina, and She. For this project, we use AOTTP electronically tagged Bigeye Tuna data. We had access to 33 tags, a mixture of pop-up satellite and implanted archival tags. The map on the left shows the tagging locations in green, the estimated tracks in blue, and the red numbered areas are the Bigeye iccat reporting areas. This effort took place between 2017 and 2020, and as you can see from the map, the tagging effort was pretty extensive from West Africa to the US, down to Brazil, and up to the Azores. These tracks were used to produce advection and diffusion parameters, which were then used in a simulation scheme to simulate thousands of additional tracks. And these tracks were then used to produce movement transition matrices of Bigeye tuna between the boxes that you see. How we actually did this was using an R package called SatTagSim, which I developed as part of my ongoing PhD work, which is designed to produce movement matrices from electronic tags. The reason we want to do this is to alleviate movement estimation issues in spatially explicit assessment and operation models. These movement matrices can be done outside of the estimation process in those types of models, and using the electronic tag information to do this is a nice way to include fishery independent information in this. Also, using simulations helps fill spatiotemporal gaps for these models, and it's informed by data that we have, movement data that we have. The simulations themselves are done from a random walk framework, which is parameterized by advection and diffusion parameters, these U's, V's, and D's that you see in the equations. The simulation scheme is both temporally explicit and spatially explicit. So we came up with monthly advection and diffusion parameters, for every month and also for every one of these Bigeye reporting areas. We did 6,000 simulated tracks, releasing 500 fish in each month, 4 simulation points per month, and 4-year-long simulated tracks. From there, we got both seasonal and yearly distributions and transfer matrices. We did not have observations in all months in all areas, so some things needed to be imputed. What we did here is we just used a global mean of the movement parameters to fill in values for these times and areas where we didn't have observation information. Now, there's other ways to do this. We could combine certain areas together, or possibly use observed parameters from adjacent areas or something like that. But for our first cut, we did something simple and went with this. What you see here, the arrows represent the advection part of the movement, and the circles are proportional to the diffusivity in these times and areas. This is what it looks like month by month, just so you can see some of the differences. The blue dots are, again, the estimated tracks for each month. And the simulations themselves look like this. What you're looking at is a 95% distribution of the 6,000 simulated tracks for each season. So winter, spring, summer, and fall. It's nicer to look at it this way than a spaghetti plot of 6,000 tracks, I think. But what stands out here is the concentrated distributions off of Northwest Africa. I will say that before we added the tagging efforts from Morocco, these distributions looked a little bit different. In fact, they looked closer to the tagging map we saw in the first slide. So I think something might be going on here with using these global mean parameters for times and areas where we didn't have observations. But for demonstration purposes, I just wanted to show you what this looks like and what you can do once you have the simulation tracks. So movement transition matrix looks like this. We have 13 areas. The y-axis represents the starting area for each simulated track, and the x-axis represents the area where it ended up in at the end of the time period that you're looking at. So this is an annual matrix, so it's simply a representation of the overall movement in and out of the particular areas. The numbers themselves are percentages. The one that stands out is that number 1 right in the middle for equatorial West Africa, where no fish moved in or out annually, according to the simulations. The other areas noted showed more emigration out of those particular areas. This is what the seasonal movement transition matrices look like. So in a seasonal fashion, when you look at a particular month, that's movement in and out of the areas that you see predicated on the month that came before. So if you look at the top right for spring, the starting area for spring would be the ending area where they were in the previous winter. And that's how you would read these. So next step, I would say that these results are preliminary. I wanted to point out that these results can be sensitive to the input data and the amount of stratification that's used. In other words, a few long tracks can be more informative than lots of short tracks. But that said, the use of simulations can extend the utility of short tracks if they were deployed in a stratified fashion in time and space across the range of the fishery. In that case, short tracks can be very valuable because you still get observation information where you need it. I think going forward we might look into using tag-informed areas instead of the iccat reporting areas. And I think this will be pretty valuable to compare with conventional tag attrition models that are being done. And finally, we need to apply this to the AOTTP yellowfin as well. I want to thank everybody for listening, and especially thanks to the AOTTP tagging participants. I think this is a fantastic effort, and I'm just really happy to play a part in this work. So thank you very much.